Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll work out a numerical example on thick cylinder. A thick cylinder with internal diameter 200 mm and 50 mm thick wall is subjected to an internal fluid pressure of 50 megapascal. Find the maximum Hope stress and plot the variation of Hope stress and radial pressure across the cylinder wall. Also find the longitudinal stress induced on the cylinder wall. So the thick cylinder, which is having internal diameter 200 mm and 50 mm thick wall, is subjected to 50 megapascal internal pressure. So you need to find out the maximum Hope stress and plot its variation and also the radial pressure variation across the cylinder wall. So inside diameter is given 200 mm. So you can find out the inside radius as 200 by 2 or 100 mm. And thickness of the wall is given. So inside radius is known. Thickness you can add to the inside radius, which will give the outside radius R0. Inside pressure is 50 megapascal. 50 megapascal. And outside pressure is not given. So in this case you can assume outside pressure P0 as 0, because without that we will not be able to calculate the Hope stress. So outside pressure is taken as 0. Even though it's not mentioned, we have to take at least this data is required to solve the problem. So without that you will not get the two equations. So only if you get two equations, because we need to find out when you use a Lemay's equation, we need to solve A and B, the constants A and B. So to solve those constants, we need at least two pressures or one pressure and one Hope stress values. So here only one pressure is given, Hope stress is not given. So maximum or minimum Hope stress should be mentioned. So only one pressure is given. With that we cannot solve problem. So let us assume that external pressure as 0. So we know that for a thick cylinder the pressure variation is given by B by R square minus A. Now when R is equal to Ri, we know the pressure. So inside radius, corresponding to inside radius, internal pressure is known. So inside pressure is 50 megapascal when radius is 100 mm, that is inside radius. On the inner surface the pressure acting is 50 megapascal. So when R is equal to Ri, the pressure is 50. So you are getting one expression for radial pressure. So 50 is equal to B by 100 square minus A. And also we know the radial pressure when R is equal to R0, pressure is 0, that is external pressure we assumed it is 0. So R is equal to R0, pressure is 0. So you can substitute R0. R0 in this case is 150 and pressure is 0. So 0 is equal to B by 150 square minus A. So these are the two expressions which you are getting. Both the pressure equation we have used. Okay. Now to solve for B and A, you can subtract these. 2 you can subtract from 1. So you can subtract equation 2 from equation 1. So you will get 50 minus 0 is equal to B by 100 square minus B by 150 square. Minus A, minus of minus A plus A will cancel. So A will cancel. You will get an expression in B. So you get 50 is equal to B by 100 square minus B by 150 square. So by solving this you get B as 900,000. So this is a constant B. Now once you get this constant, you can substitute this constant in any one of this equation which you have. So B is 900,000. You can substitute in this equation or the second equation. In this case, because denominator here we have 100 square, so this equation will be easy. Here you have 100 square, which is 10 raised to 4, 900,000 divided by 10 raised to 4 will give 90. So this is going to be 90, and minus a if you take to the left hand side, you will have 90 here, and 50 you take to the right hand side, you get minus 50. So 90 minus 50 will get a as 40. So if you substitute here also, you will get a. So whichever equation you want, you can use it to find out the another constant a. So a will get 40 by substituting in 1 or 2, you will get a as 40. Now the constants a and b are known. Now you can use Hooke's stress equation to find out the stress at any radius r. So we have the Hooke's stress expression in sigma c as b by r square plus a, and b is 900,000 and a is 40. So sigma c is 900,000 by r square plus 40. Now substitute r as Ri, which will give the inside Hooke stress, and when r is equal to Ri, this is going to be maximum, as this is having a plus sign here. When r is equal to Ri, when it is minimum, you will always have maximum Hooke stress. So inside surface of a thick cylinder always have maximum Hooke stress. So you can find out the maximum Hooke stress by substituting inside radius, that is 100 mm. So sigma c maximum is when r is equal to Ri, or when r is equal to 100 mm. So substituting that, you will get the sigma c as 130 megapascal. So this is the maximum Hooke stress, and it acts on the inner surface of the cylinder wall. When r is equal to r0, that is 150 mm, you will have minimum Hooke stress, or substituting that, you will get the Hooke stress as 80 megapascal. So outside Hooke stress is 80 megapascal. You can also find out this by another equation, because we know the relation between sigma c and pressure. So we know sigma c is equal to PR plus 2A. Radial pressure plus 2A will give sigma c. When we derived Lemay's equation, we studied that Hooke stress is given by PR plus 2A. So radial pressure outside is 0. Okay. So sigma c is PR plus 2A. PR is 0 outside, plus 2A. A is 40. So 2A is 80. So we'll get sigma c as 80. Longitudinal stress induced on the cylinder wall, you can calculate as Pi Ri square minus P naught R naught square divided by R naught square minus Ri square. In this case, P naught is 0. Pi is 50, Ri is 100, and R naught is 150. Substituting that, you will get the longitudinal stress as 40 megapascal, which you can see here. It is 50% of the circumferential stress on the outside surface of the wall. So in case external pressure is 0, you will get the longitudinal stress as half of the circumferential stress acting on the outer surface. Now you can plot the variation of Hooke stress and radial pressure across the cylinder walls. So I have shown this inner radius Ri and outer radius R0, that is 100 mm and 150 mm. So this is the cylinder wall thickness, it's 50 mm thickness. Now inside surface you will have a Hooke stress of 130 megapascal. So that is a maximum Hooke stress, 130 megapascal. When it comes to the outside of the cylinder, the Hooke stress is reduced to 80. So these two values we have calculated, 130 megapascal and 80 megapascal we have calculated, and we know the variation is parabolic. So you draw a curve from 130 to 80. Okay. So approximately every 100 megapascal you represent by 1 centimeter, you will get 1.3 centimeter. Approximate length you can take. So proportionate, it should be proportionate. So this 1.3 centimeter or 13 millimeter if you take, this you will get 8 mm. Okay. So here you take 13 mm, here you take 8 mm, so that will get a proportional height for this graph. So now you plot a curve. Okay, so that will give the variation of hoop stress across the cylinder walls. Now any radius you can find out this hoop stress. That is not required. You need to show the variation showing the maximum and minimum values. Since the hoop stress is shown in this direction, we cannot plot it here. So I have plotted it down, radial pressure, and it's also negative. It's you can show it downward only. That is better. So radial pressure is inside it's 50 megapascal, and outside the radial pressure is 0. So 50 to 0 it varies parabolically, and we have shown it downward. Okay. So also radial pressure is compressive, so you can show it downward only. That is downward indicates negative, and hoop stress upward I have shown that it indicates positive value. So this is how you plot the variation of hoop stress and radial pressure across the cylinder walls. You can show this entire cross section of the cylinder by completing the circles, but it is not required a section. You can show, and the cylinder thickness, the wall thickness is important. Show the variation of hoop stress and radial pressure across the cylinder walls. That's all for today. Thank you for watching.